recording is about to start. That's good. It's recording. Okay, and then we go over to share screen. And that should, if everything works, can you see the screen? Attendance, yes, fantastic. Good, we are in business. That's excellent. Don't forget to do the attendance. And Wisdom, I'll try to find the link for the group chat. But as I said, I think the name of the group chat is Kent Biology 2020. And you probably find that on Facebook Messenger. Is Kent Biology 2020, is that the right group chat? I don't want to send you to the final year group chat. Biology Kent 2020, that's the one, yeah. Thanks, Gertie. Good. Excellent. Shall we crack on? Because as people pointed out, it's soon gin o'clock. And I think I've done enough damage for 1 week. And you're probably knackered as well, aren't you? Right, let's get started. So, welcome to our final session. No. Pizza Fund. Is absolutely for you, but please, guys, go easy on people. I'm sure they don't do it deliberately if the microphone is open, and it can happen to the best. I have done it. Okay, so last lecture for proteins, and I want to go a little bit over what we have discussed previously, because I got a few questions from people, and I think that's absolutely great. That you ask questions, that is the sign of very intelligent people. One of the questions was, what about these Switter iron? Now, just to repeat, the Switter ions is when the N-terminus and the carboxy terminus are charged. So if they are charged, and the N-terminus, the amino terminus, would be charged, how? What would be the charge on the N-terminus? Under physiological conditions. If you look at, for example, an amino acid, it would be charged positive. Absolutely right, because the amino group could accept another proton and therefore would be positive. And on the other end, it would be negatively charged because the carboxylic acid group would lose the proton and will become negatively charged. And if you look at any amino acid, under physiological conditions, it will always have a positive charge at the N and a negative charge at the C terminus. Physiological conditions is if you are around, say, pH 7-ish, something like that. Then any amino acid will be charged. Overall, the amino acid will be neutral because you have positive and the negative charge. So overall, the amino acid will be neutral. But if you look at the amino terminus, it will be positive. And if you look at the carboxy terminus of the amino acid, it will be negative. Likewise, with any kind of protein that you have, so let's just simply draw a protein like that. Every protein has an amino terminus and a carboxy terminus. And under physiological condition, again, the amino terminus is positively charged, the carboxy terminus is negatively charged. And that is the carboxylic acid and the carboxy terminus. Very important, under physiological conditions, the backbone of the peptide or the polypeptide or protein, and very often people use the term polypeptide and protein synonymously. The backbone of the polypeptide is not charged. Not charged at all. There are sort of occasionally some partial charges floating around, but it's not charged. The charges that a protein can get are then predominantly from the side chains. And again, as I said, physiological conditions, pH 7 and normal temperature. You can force charges into the backbone of the polypeptide, but you need really, really brutal conditions, and that's not something that we are looking at. So the charges are overall, the charges of a polypeptide chain are dictated by the amino and the carboxy terminus and by the charges in the side chains of the amino acids that you have. So it can be positive, then there can be a negative charge, and so on and so forth. So if the R group is charged, the R group, the side chain of the amino acid is not part of the backbone. Remember, the backbone is the peptide bond, is formed by the peptide bonds. And let me just quickly see if I find the right picture for that. Let me see. Yes, for example, this one. So what you see here is really what I'm talking about. The backbone is really, let me see, is this part, how do I do that? Is this part here, right? And from this backbone, there are the side chains sticking out. And that is, for example, a typical beta sheet here. And you've got these big blobs here. These are the side chains. The backbone is formed by the peptide bonds. And we talked about that previously. The peptide bonds are not charged under normal physiological conditions, i.e. pH 7, but the side chains can be charged. And this is then what contributes to the charge of a protein. So that's quite important, and I don't want you to mix that up. Okay, we talked a little bit about how proteins fold, and I think the really important message is, so how proteins fold. How proteins fold into the native state. The native state is the biologically active state, where the protein can fulfill its biological function, and the information for the folding process is encoded in the amino acid sequence. So really, the amino acid sequence, the primary structure, is all the protein needs to know in order to form eventually. So if you've got your amino acid sequence here in your primary structure, that is really all the protein needs to know in order to form the correct native structure in which it is active. And there could be, for example, here could be a helix, there could be some beta sheets here, something like that. And that is the native structure. However, sometimes there are also environmental factors that help the protein to adopt this structure, so can help. But I don't want to go into detail what these factors are. Oh, fantastic. Somebody recognized my drawing. That's I'm very pleased about that. So there can be other factors in the cell that help the protein to adopt this native structure. They are actually called molecular chaperones. Molecular chaperones. Okay, so this is how proteins fold. What I now want to do is I want to spend a little bit more time on how we analyze the proteins. And was it only yesterday? I talked about you will learn about molecular chaperones at a later stage, I promise you. And predominantly, I guess, in BI 302 in the cell biology module. I told you that we can analyze proteins, and one of the most common analytical methods is to separate the proteins, by size. And I told you that with the proteins, there is a certain problem because they can come in all sorts of different shapes, and they have different charges. And I told you just about the charges. These charges come from the side chains of the amino acids. And since the proteins have all different side chains, proteins can have overall very different charges. The way we analyze proteins very frequently is through electrophoresis. Electrophoresis, where we basically make the protein move around in an electric field. So if we've got an electric field, let's say we have a positive charge here and a negative charge here, and we put a protein into this electric field, let's say we have a protein that is overall negatively charged, positively charged. What will happen is that this protein will move towards the negative charge. And if we have a protein that is much bigger, for example, and also has a positive charge, a bigger protein, because it's so much bigger, will move slower. Big proteins move slow, small proteins move fast. There are, obviously, we need to have not just sort of an electric field with positive and negative charges. We also need some kind of matrix in which the whole thing happens, where we can run these proteins, and it's sort of a solid support, the matrix, solid support. And actually, when you have that in your hand, which I would not recommend, but this solid support is usually really like a gel, you know, when you do vodka gels or something like that, some jelly-like substance. This stuff is just sort of support that it doesn't float away the protein. Now, when we run DNA gels, the support matrix is this compound called agarose, which is a gel, and it just simply forms sort of very large pores, if you like. And the protein and the DNA then is squeezed through these large pores. So the matrix for the DNA gels is agarose, where we run the proteins in. The proteins use a slightly different matrix, and that is made up of a substance called polyacrylamide. And you probably are familiar with that, because polyacrylamide, if you have it very, very small pores, polyacrylamide, actually you can wear it as clothing. But if you have it more jelly-like, then it forms similar to agarose, sort of a mesh, but the pores are much smaller, because usually proteins are much smaller. And what you very often find is that protein electrophoresis is referred to phoresis. That's the one. Is referred to as PAGE, which simply stands for polyacrylamide, polyacrylamide gel electrophoresis. So you see that very often, and you can look up this term on YouTube, and you find loads and loads of videos, some better than the other. The basic, how shall I say, the important thing really is that polyacrylamide forms sort of a network of little pores where the protein can squeeze through. If you have got extremely large proteins, then the pores are too small in polyacrylamide, and then you would use a different matrix. Sometimes very, very large proteins actually you analyze with agarose gels, but that's not terribly common. When we are talking about the size of a protein, we usually talk about proteins or polypeptide chains, proteins in the range of, let's say, 100 amino acids to several thousands of amino acids. So proteins can be anything in there. And when we are talking about the molecular mass of a protein, this is very often not stated as gram per mole, as you would hope. It is usually referred to as a very similar unit. Instead of gram per mole, people speak of Dalton. So Dalton, which is abbreviated either as DA or D. And there is a sort of a rule of thumb, if you like, that each amino acid roughly, on average, has a molecular mass of, well, the rule is 110 gram per mole, or you can also call it 110 Dalton. So if you've got a protein with 100 amino acids, the molecular mass is usually referred to as roughly 100 times 110. That would be, what is 100 times 100? 10,000. So that would be roughly 11,000 gram per mole, or 11,000 Dalton, or people use this abbreviation as, just simply they write it as an 11 kD protein. So now we've got that out of the way, and you can easily calculate, for example, 45, a protein with 450 amino acids, that would give you roughly a 50 kD protein. And kD in this case means kilo, so kilodalton. Okay, so we go back to our electrophoresis, and we can, in principle, distinguish between two forms of electrophoresis when we're talking about proteins. Let me write that down. We can distinguish between two forms of electrophoresis. In one case, we would sort of denature the protein denature the protein and fold it up and unfold the protein. Unfold the protein. So it is totally open and exposed, if you like. And I told you that proteins don't like that because they've got these hydrophobic areas and they would stick together, these hydrophobic areas. And therefore, we use a substance called SDS, sodium dodecyl sulfide. Sodium dodecyl sulfate. Which is a detergent. It's an ionic detergent, and it renders and it sticks to amino acids and is negatively charged. And in order to get the protein unfolded, we would use heat. We would boil the protein in the presence of this SDS. Nobody actually will ever mention the full name. It will always be referred to as SDS. But obviously, in an exam, I would write it out, and you would need to know that SDS is the same as sodium dodecyl sulfate. So we would denature the protein and unfold it. In this case, the only thing that actually matters for moving, the only thing that matters is the actual size of the protein. That determines how fast the protein moves through the gel. Moves through gel. What doesn't matter is the charge, the original charge. Original charge. That doesn't make any difference anymore because it is totally compensated by all these negative SDS molecules or the shape of the protein. Again, the shape does not matter in this case because we have totally unfolded this protein. And that is denaturing gel electrophoresis, which needs SDS and heat. So the gel is totally, how shall I say, destroyed. It has no longer any biological activity when we have finished with it. The gel is totally, what's the technical term? Fluffed? Yeah, probably. In contrast to that, we can also run a gel. We can also do electrophoresis. Electrophoresis with polyacrylamide gel electrophoresis. We can do that under what is called native conditions. This means we make use of the fact that the protein is charged somehow, and usually all proteins are charged. So what we do is we have an electric field, and we would probably place, and let me draw it the other way around. Let me draw it like negative and positive. We would probably place our protein, which is in its correct biological function, and it still has, for example, its correct charges. We haven't messed with these charges. So this protein here would have an excess of 3 positive charges. So if we apply the field, which direction would the protein go? Would it go up or would it go down in this case? If we've got positive charges on the protein, it would, of course, it would move upwards to the negative charges because positive goes to negative. On the other hand, if we had another protein, and let's say we have negative charges overall from the side chain, then this would, of course, go down to the positive electrode. So we could separate the proteins just simply based on their native charges. We can separate them depending on the charge. But we would not get a lot of information about the size of the protein because the native polyacrylamide electrophoresis, all the factors play a role. So what matters for the movement is the charge of the protein from the side chains. It's the size of the protein and it's the shape of the protein. But what we would get, what happens if the protein is neutral overall? Where would the protein move? Let's do a neutral protein here. So we have negative and a positive and a negative and a positive. You see the charges neutralize. What happens in this case? Which direction would the protein move? And now, what I want you to do is I want you to type that, but without the question mark. It would not move. It does not move. It just simply stays put because it doesn't know where it wants to go. There is no way it's moving, and it just simply doesn't move. It stays there in the middle, sort of. Does that make sense? So, what we would get in this case, when we use native page, is the protein still active? Or would it be possible that the protein is still active under native conditions? Could we just simply take this protein and, do an activity test? Shakil says, maybe. Ellie says yes. And Edith says, I want to say no. So if we haven't really sort of bullied or abused this protein here, we run it under native conditions. So there is a good chance, actually, that under native conditions, keep the protein active. And what you sometimes can do is even you can run a native gel, and then cut out the protein You can separate it from others, and the protein then can still fulfill its biological function. Its biological function. That is what I mean by active. That is possible if you run it under native conditions. It is active, it maintains its activity. That is native gel electrophoresis. There is, of course, under denaturing conditions, the protein will not be active. The protein is basically destroyed because we have totally unfolded. So let's quickly do, let's simply, there are lots and lots of different ways to separate proteins. If you don't need the protein in an active state, if you just want to analyze the protein, then you use SDS page. If you need to have the protein afterwards in an active state so that it can still do something, then you would have to use native gel electrophoresis. SDS page is usually much easier. So SDS page is easier to perform because what you do, you don't have to worry about which way the protein moves, up or down. It will always move. If you've got negative up and positive down, under SDS page, the protein will always move down because the protein is negatively charged. Okay? Now, let's do a little, let's run a gel. Let's run a gel with an antibody. Antibodies are complex molecules, are complex proteins, which are in the quaternary structure. So quaternary structure means there are several. SDS page uses polyacrylamide gel electrophoresis as well. In one case, you just simply don't do anything to the protein. It is still in the polyacrylamide matrix. You don't do anything to it, that's native. If you treat it with SDS and heat, and then run it in the polyacrylamide matrix, then the protein is totally knackered. Okay? So antibodies are quaternary structure, and they are actually made up of 4 different or 4 polypeptide chains. And an antibody usually looks a little bit like that. And let me take this. So it has 4 chains. And what you want to use, if you just want to analyze the protein, when you don't need any activity, you use SDS page. That's the easiest way. These antibodies are held together by disulfide bridges. Something like that. Looks a little bit like that. My drawing is awful, but it basically you get the gist. It's made up of 2 times a heavy chain and 2 light chains. And that's a disulfide bond. These SS are disulfide bonds from cysteine residues. The light chain, each light chain is about 220 amino acids, roughly. And the heavy chain is about 450 amino acids. So for the total antibody that you get here, you would get 2 times 450 and 2 times 220. So you would get roughly a molecular mass of 150 kilodalton. How did I do that? Well, 450 amino acids. If each amino acid is 110 molecular mass, then we've got roughly 50 kilodalton for a heavy chain. And for a light chain, we have roughly 25 kilodalton. So you have got 2 light chains, that gives us 50, and 2 of the 50, that gives us 150 kilodalton. You don't need to know the numbers, but I want to show you something that's happening here, or that we can do with it. So what we can do is we can treat this antibody that we have, and we can run this under SDS page. So we heat up the antibody, heat plus SDS, and we run it onto a gel. These gels are usually, they look like that. Let me try to get this nice, because it's Friday evening and you really deserve the best. Ha! Good. That is our gel. With an SDS gel, we always have the negative charge on top and the positive charge at the bottom. So we run our gel, and we would find that the protein runs at about 150 kilodalton. How do I know that, actually? We usually will use what is called marker proteins, where we exactly know the size of the proteins. We run them together in a different lane, where we know exactly how big the protein is. So here, this would be, for example, say 300 kilodalton. This might be 200, this might be 100 kilodalton, maybe this is 50 kilodalton, this might be 25 kilodalton, 10 and 5 kilodalton. So this would be a marker which is made up of different proteins that we can run on the gel. Does that make sense? Excellent. And if we run our antibody, we will find it's running about here. As I said to you earlier, one amino acid is roughly 110 Dalton. So you just simply multiply it by 110, then you get these rough numbers. each marker protein is a different protein. Absolutely, that's right. And you can buy mixtures of these marker proteins so that you can just bang them on this gel. You treat them exactly like your antibody, for example. You also heat them and add SDS, and they run, and you know exactly the position. Thank you, Evie. Exactly. So this is our protein, our antibody. Now, I told you that the antibody is made up of 4 subunits, if you like, of the 2 heavy chain and the 2 light chains. And these chains are connected by these disulfide bonds. So there is disulfide bond between the heavy chains. And of course, there is disulfide bond also between the heavy chain and the light chain. These disulfide bonds are pretty stable. They only form under oxidizing conditions. They are basically 2 cysteine residues that form a bond like that. 2 cysteine residues. This is actually called cysteine. If you've got 2 cysteine residues, they are forming a cysteine. Confusing, I know. Now, if we treat our antibody with a substance that breaks the disulfide bonds, so disulfide bond breaker, and that would be a substance that is highly, what's the opposite of oxidizing? Disulfide bonds form under oxidizing conditions, and the opposite of oxidizing is reducing. So we use a reducing agent. And one of the most common reducing agents is called beta-mercaptoethanol. Beta-mercaptoethanol. Or just simply beta-ME, that's a beta. The structure of which is just simply an ethanol, OH, and it has an SH group here. Mercapto means sulfur. So that is beta-mercapto. Beta-mercaptoethanol will break the bonds. Do not drink beta-mercaptoethanol. Mind you, you wouldn't drink it because it stinks of rotten eggs. Ethanol, yes. Beta-mercaptoethanol, toxic. Forbidden shots, absolutely. So, what will we see if we treat? Yes, you will die. What will happen if we treat our protein, our antibody, what will happen if we treat the antibody that we had here with SDS only? And what will happen if we treat it with SDS plus beta-ME? Will we still see our 150 kilodalton antibody. No, you are absolutely right. Instead, what we will see is we will see a very strong band at 100 kilodalton. Oh, sorry. Very strong band. I should take that away. Very strong band at 50 kilodalton. That's our heavy chain. And also a strong band. Where is this strong band? If you look at what I just told you, where would be this smaller band here? This one here. Where's this? Anyone? Hazard a guess? No. This will be our 25 kilodalton bands. This will be the light chain. That's the light chain. So by running basically my antibody on an SDS gel, I can get a lot of information about it. I run it under reducing conditions. That is called reducing conditions because it contains a beta mercaptor, ethanol. That's the reducing conditions. I separate the subunits that are held together by the disulfide bonds. If I run it under what is called oxidizing conditions, I get the full-length protein where the subunits are not separated. So one thing that is really important is that SDS on its own, SDS does not break disulfide bonds. Does not break disulfide bonds. If we want to break disulfide bonds, we would need beta mercaptor ethanol. Does that make sense to you guys? So very easily you can distinguish, you can say, okay, what is the overall size of my protein? And if I have, for example, I might have something where I have subunit 1 and another subunit which are not connected by disulfide bonds. So there are no disulfide bonds. If I treat this with SDS, it will split into two different subunits as long as they are not connected with disulfide bonds. So SDS can pull them apart, but not if there are disulfide bonds. Welcome, absolutely right. So SDS page, you need SDS and heat to open up any complexes and make everything negative so that it moves in the right direction. If you add beta-mercapto, you also then break the disulfide bonds in the that holds anything together. Does that make sense? So reducing conditions is with beta-mercapto ethanol, and it breaks the disulfide bonds. If you really understand that, and I mean, there are lots of YouTube videos out there, you are on the best way of becoming a good protein biochemist. And with that, I realize it's already 6 o'clock. I do not want to deprive people more of their well-deserved Nando or their drink. Oxidizing conditions is no beta-mercapto. Reducing conditions is with beta-mercapto, because you reduce this disulfide bond. So it's 59. All I can say is thank you very much for listening to me. If you've got any questions, I'm very happy to answer them via email or through group chat or something like that. So hit me up with that. But proteins, you should now know a little bit about proteins and how to analyze them. And in the BI 308, then we will do a little bit more about the sizes. You probably noticed that I've drawn these sizes here in a really funny way, which is not linear, but I'll talk about that in BI 308. So it's enough for today. Let's end, and I shall see most of you then in the practical on Monday or Tuesday, which is the BI 308 practical. Have a great weekend, and thank you for watching and listening. Take care. Bye. Be good. Don't do anything I wouldn't do.